Hey, hello everyone, and welcome to the Zero to CCI webinar or Zero to Lab webinar. I hope you guys can see me. You can let me know into the chat. And what we are going to do in this webinar is we are going to make sure that we understand some basic idea how the technologies work. Just a second. Yeah, let me share this screen again. All right. So in this webinar, we are going to talk about one specific technology, what we are going to cover in our CCI course, which is MPLS. So we have this program created just keeping one thing in mind, labbing and having a lots of hands-on. As you know, the name is Zero to Lab. So we want to make sure that everything that you need to learn about zero to the CCI exam, you will get it here, and you will get the ample practice as well for the same thing, right? So we want to make sure that once you complete this, you should be able to go for the CCI exam and pass the exam easily. So this particular implementation or the things that I'm going to show you today is just a glimpse of what we are going to cover. Of course, we have lots of topics in CCI, and we want to make sure that everything is properly covered. And if you find this useful, you can actually go and actually purchase this course if you like it from the link that I have just pasted, or you can also actually book a call in case if you need a little bit more information about this, or if you want to discuss about this, you can book a call with my partner Christian, and for that also I have pasted a link, so you can actually use one of these two links to find more about this course and all the details and all the questions that you may have. You can actually have a 1 hour uh, meeting with Christian, and you can ask him everything that you need to know about this course, right? So this particular session, we are going to keep only technical. I just want to show you something that a glimpse of what you will get into the course, and then of course, when you have more questions about the pricing plans or the structure and everything, you can book a call. And if you like it, then you can directly, of course, book the course as well for yourself. So first of all, let me ask you if you guys can hear me properly. So if somebody can let me know into the chat if I am properly audible. Just chat, just comment yes. Okay, thanks. Uh, Thanks, Leroy, for the confirmation. So today I'm going to discuss about MPLS, and MPLS is one of the technologies which is generally have been part of CCI for many years, and it is one of the technologies that you will see implemented on all kind of networks. So if you have a service provider network, definitely you will be dealing with MPLS. But even if you are working in a production environment, you will see that MPLS connections are the most secure, most reliable connections, and more stable connections. So they become extremely useful when you want to implement them. So before we get into the details of configuration and we get to the CLI, I want to discuss a little bit about what exactly are the components of MPLS. So if we go to our OneNote, so I always divide MPLS configuration into three phases. So what happens is that when you want to have L3 VPN connection into multi-protocol level switching, you always configure the service provider network first. You need to make sure that proper labeling is configured. So that is phase one. And then phase two is the peering with the customer. So you want to, of course, you want to enable customer or allow customer to have communication between two different branches. So the customer will actually connect to the provider edge router. So we call it the provider edge or PE router, connecting to the customer edge or CE router. So the PE to CE peering, so that we can get the routes from the customer before we can send it to the other side. That is the second part. And last phase is, of course, to exchange that traffic or exchange those routes with the other PE router on the other hand. So that is the PE to PE peering. And then, of course, the route exchange. So these are the three phases. We will go into the details of these things. But before we get there, of course, we want to understand what exactly is MPLS in case if we don't have any idea about MPLS at all. So as we always often see this keyword, uh, we use the keyword L3 VPN for MPLS. So MPLS also has L2 VPN implementations, although they are not part of CCI enterprise infrastructure. If you go for CCI service provider, you will see L2 VPN as well. But L3 VPN is one of the very common application of MPLS. But before we talk about the application itself, what do we mean by multi-protocol label switching? So when we think about the keyword label switching, How is it different from our traditional routing, right? So in traditional routing, what happens? You receive a packet to the router, and then you have a source IP address and you have a destination IP address, along with other fields, of course, in the packet. But these are the more important fields that which source you are coming from and where do you want to go. So source IP address and destination IP address. So in traditional routing, we check the destination IP address and we actually compare it against our routing table, or more specifically, we compare it against our FIP table, right? Forwarding information base, which is the cached copy of routing table into the hardware. So we check against it routing table and we see that how do we go to this destination network. And when we find a match, we actually send the packet to the next hop, right? That's your traditional routing. Now, when you perform labels switching, what you do is you take the packet, which has the source IP address and destination IPs and everything, and you actually impose a label here. So there will be a number, a label number, and this is called a label. And you will have a label which is prepended or imposed before the packet, and then you send the packet to the router. So instead of checking the routing table, you are going to check something called LFIP, label forwarding information base, right? So it's just like your forwarding information base, but for the label. And what you're going to do is you're going to check the label forwarding information base, where you will have some information like this, that if the incoming label is X, that as you can see here, then the outgoing label for this will be Y, and then we need to send it out with the exit interface, whatever it is, right? So interface will be, the name will be like say gigabit Ethernet 001, and then the next hop IP address for that. So where do you want to send it? The next hop IP address will be here. So what happens is that when you receive a packet with a label, you're going to swap it from one label to another one, and then throw it out this next hop. That's what we call a label switching or label swapping. So of course, label swapping is not something which is better than traditional routing. Some people think that if we are using labels, then the network is faster or it is more efficient. It's not actually about the speed or efficiency. The label swapping is used to keep your service provider network, the core part of your service provider network, BGP free, because you are providing services to the customers, and customers will be sending you lots and lots of routes so that they can be sent to another location. For example, think about this customer. It has one location CE1, customer edge 1, and one location CE2. They could be in different cities, even different countries, right? And we are receiving hundreds of routes from this customer, and the customer is expecting you to send them all the way to the other branch, right? From branch 1 to branch 2. And you are a service provider, so you may have multiple customers, and all these customers might be sending you hundreds and hundreds of routes, and you need to send them to the other side. So what you want to do is you want to get these routes into the BGP and then transport them all the way to the other P router. You don't want your internal routers like this P router, which is simply a provider router or service provider router. This one should be kept BGP free, and it should not be bothered with all these thousands of routes coming from the customer. It should only know about the routes which are internal to the MPLS backbone, internal to the service provider network. And I'm using a single router here, but there it could be many routers, because let's say if provider edge 1 is in London and provider edge 2 is in Paris, then of course they will not be directly connected or just connected via one router. There could be multiple routers there, right? So to go from one location to another location, we want to keep the core of your service provider network BGP free, and that's why we use label swapping. Label swapping is not used to make it more efficient than your traditional routing, but just to keep your core BGP free. How do we do that? We actually first of all do one thing, is that from the loopback of P1 to the loopback of P2, the loopback IP to loopback IP, that communication should be happening with the labels, not without the label. So for that, we use some protocol for generating and distributing labels for every network we have. And that protocol is called LDP, or label distribution protocol. So of course, when you come to our CCI class, you will see MPLS is actually for 3 to 4 days. We don't actually complete this in 30 minutes. We want to make sure we go in depth. So today is just a basic glimpse that what you will actually be able to achieve once you join our course. So we will not be able to go into the very much detail of everything that we go into the actual course. But I want to show you the end result, that how it would look like, and how the routes will be exchanged between different branches of the uh, same customer, right? So customer 1, branch 1, and the same customer 1, branch 2, maybe 2 different locations. But the protocol LDP, we will go into in-depth detail of this when you join the course. But basically, just to tell you what it does is that it generates labels for your service provider network. So anywhere you want to go within the service provider, like from PE1 to PE2 and vice versa, you will be doing label swapping and not using the traditional IP routing, means using the destination network. That's why we need to make sure that PE1 and PE2 should be reachable from each other. Some kind of IGP should be there in your service provider network. And then you will configure LDP to activate label swapping, so that when PE1 is sending traffic to PE2 or PE2 is sending traffic to PE1, it is label swapped instead of using traditional routing. So that's what you see here as the phase one. Phase one is some kind of IGP in your service provider network on those three routers, PE1, PE2, and P router. And then we will activate LDP there as well, right? So let's go ahead and do this, and then we'll see the solution for this, right? Like the output of that. So PE1, P, and PE2 router. These are the service provider routers. And as you can see into the diagram, I have already configured IP addressing. So P1 side is 10.1.1.1 and P router is 10.1.1.2. So it's the one broadcast domain. And then between P router and P2 router, we have 10.1.2.0 network. So dot 1 and dot 2 on both sides. And we have loopback interfaces on P1 and P2. Loopback P1 is 1.1.1.1 and P2 of course is 2.2.2.2. So after we configure some IGP, you can decide what you want to use: OSPF, RIP, EIGRP, even static routing, doesn't matter, as long as you can provide reachability between these two loopbacks. Loopback to loopback communication between P1 and P2 should happen. That will be your IGP. And then we will see that we will activate LDP, so that this communication, the same loopback to loopback communication, will be happening over the labels, right? So let's go ahead and configure some IGP between P1 and P2 and the P router. So starting from P1, if I check show IP interface brief, exclude unassigned, which interfaces have IP addresses. So we can see that this 10.1.3.1, this one is going toward the customer because it is Ethernet 00, and we can see P1 Ethernet 00 is going toward the customer. So we do not activate our IGP on this interface. This is the link which will be configured with the VRF. So we configure a dedicated routing table toward the customer, which is keeping the routes only for that customer, which is called VRF. So we are not going to include this network into our IGP. So the only network we need to include is the loopback and the Ethernet 0/1 of PE1, which is 10.1.1 network, right? So let's go ahead and configure some routing protocol. Let's say OSPF. So router OSPF1, the network you want is 10.1.1.0. Wildcard mask to match the first three octets. And let's keep it simple. Let's use just flat area structure, area 0. And same thing for our loopback also. So that is also an area 0, right? By the way, this wildcard mask just tell you that how many bits you need to match or you need to compare with the interface to activate the routing protocol. So many people get it wrong. So many people think that, oh, this is telling us that what will we be advertising as a subnet mask. No, it has nothing to do with that. It is just telling OSPF where to get activated, which interfaces to get activated, how to find the interface where OSPF will be activated. So when I'm saying that the first three octets are 0, first 24 bits are 0 in wildcard mask, that simply means that we are telling to OSPF that whatever you see here, the first 324 bits, go and compare it to every interface. And if you find the interface with the same first three octets, then activate OSPF there. That's what we are saying. That's why you can be more flexible here. You can see that I'm using all 0 here. And what we are doing here is that we are matching exactly this IP address 1111, right? So this is the one. This is just a quick side note about OSPF, nothing to do with MPLS though. So let's go to P router, and sorry about that. We have to skip this. By the way, if you do a no IP domain lookup, then you will not see this issue. What happens is that if you type, you do a typo, router thinks that you are trying to type some name and it tries to find a DNS server to fix it. See, right, so this is the P router. Let's see what IP address we have. Only 2 IP addresses, so we can actually go to .ospf1 network 10.1.0.0. So you can see that a single statement will activate OSPF on both of them, because I am saying that find interfaces with the first two octets 10.1. and both of them have 10.1. So OSPF gets activated on both of them in area 0. And you can see with router 1, the neighborship also comes up. Finally, on PE2, show IP interface brief, exclude unassigned, and router OSPF1. Remember, this is more of a demonstration, so that's why I'm going a little bit fast, as you can see. But when we come to the actual implementation of OSPF or MPLS in our classes, we will go in much more in-depth theoretical part as well, because theory is important before you can see the result. But here I just want to show you that what will you be able to achieve once you join the course and practice along with this, right? So that's done. Again, I did not include the 10.1.4 network because that is going toward the customer, and that we will be configuring in the P2C part, right? So after this, the neighborship between P1, P router, and P2 should come up. So currently, we are just waiting for and P2 router to come up. And what will happen with this is, let me go back here, that your IGP will be done. You will be able to ping P to P router between P1 and P2 using the loopback interfaces, and then we'll activate LDP, right? So let's go back. All right, neighborship is up. So if I go to P1, if I check show IP route OSPF, yes, I do see the loopback of PE2, right? And PE2 side, if I check show IP route OSPF, I do see the loopback of PE1. So if I ping the loopback of PE1 with my loopback address, source loopback 0, that should be successful. And if I do a trace route, trace route means how many hops I have. 1111, source loopback 0. We should be able to see that it is going to one method, one hop, right? 10, 1 to 1. So let me go to numeric. We don't want to wait for translation. Yeah, so it is going to hops. First, it is going to the P router, and then after P router, it is going to the P1 router, right? But you can see we are not using any labels. So now we will activate LDP between the service provider networks, right? So that's the second part you see here. IGP is done plus LDP. So we need to activate LDP only on the service provider network and only on the links which are going to other neighbors. Like on PE1, it will be Ethernet 01. PE router, it will be Ethernet 00 and 01, and PE2 will be Ethernet 01 again, right? So on PE1, it was Ethernet 01. The only thing we need is MPLS IP command, which activates LDP on this. On P router, it will be both interface range Ethernet 00 and 1. And the LDP neighborship will come up, as you can see. And P2 router, it will be 01 also. So in the class, I will also explain you in detail that how is this router ID is activated or elected for LDP, and how LDP works. Like LDP works on TCP port number 646. But before that, there is a discovery session, and in discovery it uses UDP port number 646. So all these juicy details will be there in the classroom for sure, right? So that you can become more confident about configuring it. But right now, you can see that the work is done. Show MPLS LDP neighbor. We can see that we have two neighbors. One is toward router 1, P1, and one is toward P2, right? And this is the port number 646 I was talking about for TCP session, for TCP connection. All right, so the difference you will see now, if you remember from PE2, when I trace route to PE1, it was going 2 hops as expected, but now we should be using label as well. So if I do a trace route again to 1111 from PE2, you can see that now I'm using an MPLS label number 16 for the LDP. And LDP labels are called transport label. So we are using transport label 16, and then we are sending it. You can check it with the show MPLS forwarding table. And you can see that if I'm sending traffic to 1111, I will be using the outgoing label 16, right? So I will be sending the packets to the P router with the label 16. And when the P router receives the packet from PE2, so basically we are pinging from PE2 to PE1. So we send the packet with the label 16 to P router. And what does the P router do with the packet coming with label 16? If we go to the P router and we check show MPLS forwarding table, you can see that if I receive a packet with label 16, I will pop the label. Means I will remove the label and I will send the packet unlabeled out Ethernet 00 toward 10111, which is PE1. So the PE1 will receive our packet without a label. That's why you see here in the trace route, the first hop shows the MPLS label but the second half doesn't show the MPLS label because the P router has removed the label. And this phenomena is called the PHP, penultimate hop popping. You remove the label one hop too soon, or the second last router. And there is a reason for this again. The theoretical detail we will skip for today. We'll just see that the overall result that we will see, and enough information so that we can understand how the complete communication will work. So congratulations, phase one is done. Now your service provider network is going loopback to loopback between P routers using the labels, right? And now, of course, the more important part, the second part, which is the communication between the P router and C router. So, of course, the customer has some routes and it is waiting for to send those routes to your P router so that you can send them all the way to the other C router, right? So you will need to use some kind of routing protocol between the P1 and C1 and the same routing protocol between PE2 and CE2, right? Because between PE routers, as you can see, we will be using MPBGP. But between PE1 and C1, I'm going to use EIGRP. But of course, you can use static routing or OSPF, even BGP also. And all these variations we will see in our classes also when if you decide to join the classes, right? So let's go and talk about this, the second phase. In phase two, we need P2C routing. So what do we mean by VRF creation and interface association to the VRF? So let's talk about these 2 points. Let me go back to the diagram and let's actually select this. All right. So just a second, let me clean it up a little bit more so that we can understand it properly. All right. So we need some kind of routing protocol here between P and C, and I'm going to use EIGRP here. But we are going to configure this interface of P router into a dedicated routing table, which is called VRF, Virtual Routing and Forwarding Table. Now, what is VRF? So remember, the customer is using the MPLS services for their private networks. Like you can see, the customer is using 192.168 network, which is a private network, because MPLS backbone is not internet. It can provide internet services as an additional service, but it's not actually internet. It's a dedicated connection or a WAN connection for your private networks that you want to exchange. The problem with this scenario or this method is that if you have multiple customers, if you have another customer here, let's say this is customer number 2. So in this case, if customer number 2 also decides to use 192.168 network, then you will be using the same, you will be receiving the same network from both sides, right? Because this is a private network and every company can use it within their organization. But now the problem is that customer 1 and customer 2 are meeting on PE1. That's the rendezvous point, right? That's where there's a meeting point for them. So if we were using just the global routing table, the routing table that we always use, show IP route command, then these routes will get mixed up, right? And how would you know which 192.168 route is coming from where? And there may be other conflicting routes as well. Excuse me. So to keep the routes separate so that we can understand that these routes are coming from customer 1 and these are coming from customer 2, and we make sure that they never get mixed up, we use dedicated routing table. Excuse me. We call it like VRF1, or let's say VRFA for customer 1 and VRFB for customer 2. So then we associate the interfaces which are going toward the customer, like Ethernet 00 is going toward customer 1. Maybe this Ethernet 02 is going toward customer 2. So we associate the interface with the dedicated routing tables and forwarding tables. So what happens is that any routes coming from customer 1, they will be installed into VRFA. And any routes coming from customer 2, they will be installed in VRFB. So you can keep the routes separate, right? That's why you create VRF tables, dedicated routing tables. And every VRF have some unique properties. For example, every VRF will have a name. Like I'm using simple names like VRFA, VRFB, but of course you can have alphanumeric names, more descriptive names for your customer, right? So VRF will have a name. And then there are 2 parameters which are used by VRF. One is called RD, route distinguisher. Now, route distinguisher, as the name suggests, this is exactly what it does. It distinguishes the routes while they are traveling through BGP. Because think about this. Although you are keeping the routes into separate routing tables, so they are not conflicting. But when you have to send them to the other PE router, you will be using the common service provider network, right? Which is the common network between PE1 and PE2. And we will be configuring MPBGP to exchange these routes. So while they are traveling from PE1 to PE2, they are traveling under the MPBGP updates. So there they can get mixed up, right? So how do we keep them distinguished or keep them separate while they are transiting to our service provider network? So that's where we use a unique value called RD, which is unique per customer, route distinguisher. And this value is a 64-bit value, which is represented into the X colon Y format, where X is 32-bit and Y is 32-bit, right? So for example, if I'm using for VRFA, which is for customer one, if for VRFA, I am using the RD value, let's say for the sake of example, let's say 1 colon 1, then this value will be prepended to all the routes which are coming from customer one. And what do I mean by prepended? Means it will be placed before the route. So we know that this is 64-bit, right? RD is 64-bit. This 64-bit will be added before the IP network which you are sending. And we know IPv4 network is 32-bit, right? So the IPv4 networks that you are receiving from your customer, they are 32 bits. IPv4 is 32-bit. And let's say the network that you are getting is 192.168.1.0 network, right? That's the loopback 0 IP address of CE1. So you can see this is 32-bit and the RD is 64-bit. When you combine them, you get a unique value. You get the value 1 colon 1, which is the RD, colon 192.168.1.0. So you can see that we are adding 64 bits before the 32 bits. So overall, we are making it a 96-bit entry, right? Total 96 bits, 64 plus 32. And this entry, when you add the RD value to the IPv4 address, this is called VPN v4 route. VPN v4 route. So this is IPv4 route. This is RD. When you combine them, it is called VPN v4 route, right? It is 96-bit. And this is now unique because maybe there is a customer who is using VRFB, and that one will have a different route distinguisher. That one will have maybe, let's say, 2 colon 2. But the IPv4 address might be same because these are private IP addresses. Multiple company may be using the same. So maybe on customer 2 also we have the same network 192.168.1.0. It may happen, but you see that overall value, which is 96-bit, will be different, right? And because overall value is different, then it's a different VPN v4 route, and you can keep them distinguished while they are traveling from one location to another location, right? So this is called route distinguisher that you need to mention when you're creating VRF. Excuse me. So every VRF will have a name, will have a RD value, route distinguisher, and then it will have a couple of route targets. Now, route targets or RT values, these are also 64-bit. They are also written into the format X colon Y, but they have a different objective. Route distinguisher has the objective of keeping the routes separate while they are transiting. That's it. That's the only duty it has. But once the routes reach to the other end, let's say it is coming from VRFA from here, and then it reaches to the other PE router. The other PE router may also have many VRF tables, right? VRFA, B, C, D, many. So which VRF table should I send this route to? How do I know that? So how do I know that how to which VRF table it will come from and which VRF table it will go to? The reason I'm telling this is because the VRF name is locally significant. So if I'm using VRF A for customer one this side, I may use VRF C on the second side. Technically, it will not be wrong, although you can keep it same to avoid confusion. But I'm saying technically it's not wrong to use a different name on the other side. So how do you know that where should I come from and where do I go to? Which VRF I come from and which VRF I go to between P routers? So there you use the route target. You control the advertising and receiving of routes. So controlling advertising, which is called export, and receiving, which is called import of customer routes. Right? So, for example, in case of route targets, you will see that every VRF, let's say VRF A on P1, we'll have a route target. So let's call it RT. There will be an import value. So import, let's say, is 10 colon 10 because it is X colon Y format, right? And then we will have an IT export. Sorry, RT export, route target export. Let's say export is 20 colon 20. What does it mean? It means that from BGP, because the P2 will be using BGP to send you information, right? So from BGP, when the routes are coming in, I will check the import RT value. So I will check what RT value is associated with the route. Every route will a route target associated. And I will see if the received route has the route target 10 colon 10 and my setting is import, then I will import that route. I will welcome that route into my routing table. And of course, if it comes to my routing table, I will also send it to the customer. So customer will get it. Similarly, when I will advertise my routes from routing table or my VRF routing table to the BGP, I will associate the route target value 20 colon 20 because that's the export value. So you have to think about import and export keywords from the VRF routing table perspective. Is it getting imported into VRF or is it getting exported from VRF to the BGP? So if I'm exporting BGP, if I'm exporting 20 colon 20 RT value in the BGP and on the PE2 router under the VRF routing table A, I need to do the opposite, right? I need to do the import of 20 colon 20 and I will have to do the export of 10 colon 10. So whatever the routes I have, I will be exporting them with 10 colon 10, which will be imported by PE1 VRFA because we are importing 10 colon 10. And whatever the routes PE1 has under VRFA, they are getting exported as 20 colon 20, which will be imported by VRFA here because we are importing 20 colon 20. And that's how you will exchange routes between the customer routing tables, the dedicated routing tables for customer. So they kept it separate from the route distinguisher because they wanted to have a possibility of extranet. Means this way you can also import some other RT value as well, and then you can leak the routes between different customers, which might be a desirable thing by few customers, right? But ultimately, you need to use two values, import and export. Two things here. One thing is that you can use a keyword both, RT both, and then a value. So that can become an import and export both. Second thing that the value can be same. So you can have a same import and export value. It doesn't need to be different. But in case if you're using a different value, make sure that your import value is the export value on the other side and the other side import value is your export value, right? So there has to be a cross connection, of course, in and out, right? So you need to create a route target as well to create a VRF. So that's your first step, right? This is what I was talking about here, VRF creation. And then, of course, once the VRF is created, you would like to associate that VRF with some customer because you may have multiple customers. So I want to make sure that when I create this VRF table, VRF-A, that is associated with my customer C1. And for that, I will have to associate the interface Ethernet 0/0, this one, right? Ethernet 0/0 to the VRF. So let's go ahead and these two things, and then we'll see how does it impact. So we have to do this on both PE routers. So on PE1, let's first create the VRF. So we'll use the count VRF and some name. So let's say VRF, sorry, IP VRF and the name, let's say A. RD value, let's say 1 colon 1. And route target also, let's keep it simple. Both import and export 1 colon 1. And then we associate the interface which is going toward the customer, right? So the interface going toward customer is interface Ethernet 0/0. We can confirm this. Yeah, E00 is going toward customer, 1013 network. So interface Ethernet 0/0, we need to associate it with the VRF routing table. So we'll use the command IP VRF forwarding and the name of the VRF table. What happens is that when you do this, this network was in the global routing table. And now we are moving it from the global routing table to the VRF routing table. So the IP address will be disabled and removed. So you have to reconfigure the IP address here. This is something you should be aware of, that whenever you move an interface from one routing table to another routing table, the IP address gets removed. So you need to reconfigure it, right? Now, if I take show IP route, which is the global routing table, you see that I don't see 1013 network here, and I don't see Ethernet 0/0. But if I check show IP route, VRF-A, now I'm checking a different routing table dedicated for customer 1. And there, of course, I have Ethernet 0/0, 10.130 network, right? You can also use the command show IP VRF, and it will show you the VRF name you have, the RD value, and which interfaces are associated with the VRF. Let's repeat this on PE2. And on PE2, we can see it will be again Ethernet 00 1014 network towards CE2 router, right? So VRF A, sorry, IP VRF A, RD is 1:1, and route target will be both import export we are using 1:1. Okay. If I check Ethernet 00, this is the IP address, but it will be removed, right? Once we configure it into the VRF. So IP VRF forwarding A, and the IP address is removed. So let's reconfigure it. And now interface association is done. So now you see the last point into the steps is to P2C VRF aware routing, right? P2C VRF aware routing means that now you need to configure some routing protocol. On the customer side, it will be a normal routing protocol. Customer has no idea about MPLS, no idea about VRF. So if I go to CE1 and I configure EIGRP, it will be a normal EIGRP. But if I configure normal EIGRP on PE1 also, then it will always look into the global routing table. So if I try to go to PE1 and say network 10130 to activate routing toward CE1, you will see that it will try to find the network 1013 in the global routing table. And of course, it will not find it because we have moved it to the VRF routing table. So we have to force your EIGRP routing protocol to look into the VRF table. Hey, don't look into the global routing table, look into the VRF routing table. How do we do that? We use something called address family. We will tell EIGRP that don't look into global routing table, look into the address family VRF-A, and that's where you will find the route. So we associate the routing protocol with the VRF, or it is called VRF aware routing. So on the customer side, it will be normal EIGRP. So let's go ahead and configure it. So customer 1, CE1. So we can see that we will be configuring it on all the interfaces we have, all the network we have, 1013 network and 192.168.1 network, right? So router EIGRP, let's say 10, and network 10.0.0.0, and network 192.168.1.0. Right? So we just activated EIGRP on all interfaces, basic EIGRP, nothing is special on the customer side. But on provider edge 1, currently in my routing table of VRF-A, I don't have any routes, any EIGRP routes. So let's configure EIGRP toward customer, which is 1013 network. So router, EIGRP, and some autonomous system number. This number doesn't need to match your customer number because customer is using number 10. This one is the global one, which will always look into the global routing table. So we don't care about that. What we do care about is to force EIGRP to look into the VRF routing table. And for that, we use the command address family IPv4 VRF. And then you can see that we have to mention the VRF name. So look into VRF routing table A. And by the way, the autonomous system number should be used is 10. You see, this autonomous system number must match with what customer configured router EIGRP 10. So this must be same, and look into the VRF table A. Now, whatever you type, network command, EIGRP will go and check the VRF A routing table, not the global routing table. So we say network 10.0.0.0 will be okay. And that's it, right? That's the only network we have. And there you go. We have neighborship with our customer. Congratulations. Now you should be receiving at least one route, the loopback of customer, into the VRF routing table. So if I check my global routing table, I still don't have any EIGRP routes, only the service provider route, right? But if I check show IP route VRF A, now you see that I have a EIGRP route, which is the loopback of customer edge 1, CE1, received from the CE1. So it is coming into the VRF routing table. Let's repeat this between PE2 and CE2 also. So first of all, on the customer side, so on the customer side, if you see what networks we have, so we can see that on the customer side, we have two networks. So router EIGRP 10, normal EIGRP here, network 10, and network 192.168.2.0. And on the PE side, it will be under the VRF, right? So if I go router EIGRP, this AS number I type here is global, so it doesn't matter. But then I use the address family command to force EIGRP to look into the VRF table. So IPv4 VRF A, and the autonomous system number should be 10. This must match to the customer AS number. And I need the network 10.0.0.0 only, right? That's it. Neighborship should come up. If I check show IP route for VRF A, Yep, I have the 192.168.2.0 on the P router. So at this point, what's happening is your P to C peering is done. That means C1 is advertising, customer edge 1 is advertising its loopback 1.0 network to P1 under the VRF-A, and C2 is advertising this loopback 2.0 to P2 under the VRF-A. So the P routers have the customer routes under the VRF, but of course now we need to exchange these routes between P to P. Otherwise, we will not be able to send the C2 route to CE1 and CE1 route to CE2, because that's our ultimate goal, right? To see the loopback of C routers on each other, and then should be able to communicate as well. So now we will do the last phase, phase 3, which is the P to P communication. And for that, you can see there are two steps. First is MPI-BGP between PE routers. What do I mean by MPI-BGP? So if you remember, I told you that whenever you prepend the RD value to the IPv4 network, we create something called the VPN v4 network, right? Because it's 96 bits. So if you want to have MP-BGP between PE routers, they should be able to exchange 96 bits routes, not normal IPv4 routes, 96 bits VPN v4 routes. So we need to activate an address family between PE routers, which is the VPN v4 address family. That's the first step between PE to PE, and you must do it loopback to loopback. And that's why we already have loopback to loopback reachability between PE1 and PE2, thanks to the IGP of the service provider. So let's go to PE1 and let me show you what BGP configuration will look like. So let's say we are using BGP AS number 100, so router BGP 100. My neighbor is 2.2.2.2, which is the PE2, and the remote AS is same. It is IBGP, and I am using update source loopback 0. So of course, we will also go in depth detail of BGP in our course, and you will see all the specific things you need to learn about BGP. But once we have this, now we need to activate the VPN v4 address family, right? So we need to use the command address family VPN v4 unicast, and we just activate this neighbor. Activate. Now remember, if you don't do this, then it will be your normal IPv4 BGP. Means you can exchange IPv4 routes, that's fine. But can you exchange VPN v4 routes, the 96-bit route, RD plus IPv4? No. For that, you need to activate that neighbor for VPN v4 address family. So let's do the same thing on PE2 for 1111, which is PE1. So router BGP 100, neighbor is 1111, remote AS is 100, and update source is loopback 0. And of course, address family VPN v4 unicast neighbor 1111 activate, right? So we activated VPN v4, and now they are ready to exchange the routes. The very last point now for our practical is to do the mutual redistribution between the EIGRP we are running between PE to C and the MPBGP. But this has to be done under the VRF address family in both cases. In BGP also, we need to go address family VRF, and EIGRP, we are already using address family IPv for VRF, right? Because it has to be the same address family for the redistribution. And again, why are we doing this? Because now we have the routes in our routing table here coming from our customer, but this route is this route is installed as EIGRP route, right? When we check the show IP route VRF, we see it's a EIGRP route. So we need to redistribute this into BGP. And when it goes to the other end, it goes as BGP route. So we need to redistribute it back into EIGRP so that it can go to the customer. And from the opposite side also, we need to do the same thing. Receive it as EIGRP, so redistribute into BGP. When it reaches to the other P router, redistribute BGP back into EIGRP so that it can go to the C router. So we need mutual redistribution on the P router from EIGRP to BGP, BGP to EIGRP. But that should be under the VRF route, VRF address family, because of course the routes are into the VRF routing table. So the last point you see here is the mutual redistribution between the routing protocol we are running, EIGRP, between P to C and MPI IBGP under VRF address family. So let's go ahead and do that. So on PE1, the mutual redistribution simply means first going into the EIGRP, which is between P to C, going under the address family IPv4 VRFA autonomous system 10, and then redistribute BGP 100, right? And metric, you have to mention the bandwidth, load, delay, reliability in MTU, but you can also use just 11111, just if you are just practicing. And under BGP, router BGP 100, again, we need to go under address family, IPv4, VRF A, and here we will redistribute EIGRP 10. Remember the correct autonomous system that you're using toward the customer. You see, this is called mutual redistribution. Under EIGRP, we redistributed BGP. Under BGP, we redistributed EIGRP, right? So with this information, our mutual redistribution is done on PE1. Let's repeat this on PE2. So on PE2, again, router EIGRP 1, address family IPv4, VRF A, autonomous system 10, redistribute BGP 100, metric just 1111, bandwidth delay, load reliability MTU, and under router BGP 100, address family IPv4 VRF A, redistribute EIGRP 10. Now your phase 3 is also done. So what you have done is you have configured some kind of IGP and LDP between the service provider network so that you can do level swapping. You have configured the VRF associated the interface going toward the customer, and then configured a VRF aware routing protocol like EIGRP between PE to CE so that we can get the customer routes on the PE router. And finally, you had the MP BGP VPN v4 neighborship between PE to PE, and then mutual redistribution between EIGRP and BGP. So now if I go to CE1, I should be able to see the CE2 route. But this is the beauty of it. When I see the CE2 loopback route on CE1, it will not show me as external route, because generally what happens when you redistribute something into EIGRP, it shows it as the external EIGRP route, right? But here, even after 2 times of redistribution, one time on PE2 and then one time on PE1 and then coming to CE1, still it will show you as internal EIGRP route. How is that possible? That is possible because of carrying some extra baggage. So if I show you something interesting, current section router BGP, you see that I did not type this command, but it is taken automatically under VPN v4. Neighbor other PE router, send community extended. What this command is doing, it is sending some extra information, like an extra luggage along with your original package. And what is this extra luggage? So when you redistribute EIGRP into BGP, let's say CE2 sends the update to PE2 as EIGRP route, and then you redistribute EIGRP into BGP. At the time of redistribution, you carry some important parameters of EIGRP like bandwidth, delay, load reliability, MTU, and EIGRP AS number. All this important information is carried in an extra luggage, which is called extended community, and you send it to your PE1 as extended communities of BGP. So when PE1 receives those extra parameters of EIGRP, when you redistribute BGP into EIGRP, PE1 hands all these things over to EIGRP, and EIGRP says, oh, these all things are familiar to me. These are from my routing protocol. So it doesn't look like a redistribution. These are internal routes. So you don't, even after 2-time redistribution, you don't see external tag. You see that routes are still internal. So let's go and check it out on CE1. If I go to CE1 and check show IP route, voila, we can see that not only 10140, which is the link between PE2 and CE2, but also the loopback of CE2 I am receiving as just D route. D means internal EIGRP routes. It doesn't seem like it is redistributed. And can I reach there? Let's ping the loopback of CE2. Yes. Can I ping it with my loopback? Source loopback 0. Yeah, we have loopback to loopback communication, means we have end-to-end communication. CE2 will also show you these routes. So show IP route. We can see it is going through CE2 as well. And if I do a trace route to 192.168.1.1 from CE2 going to CE1 loopback numeric, you can see that I am using MPLS labels here. And at some point, I'm using 2 labels also. So this is also something I'll explain you when you join the class. That why do you have 2 labels? One is called transport label, one is called VPN label. One is created by LDP, one is created by BGP. So why do we need 2 labels? That is something we'll learn there. But today I just wanted to show you that what you will be able to achieve. And then in exam, if you see a VPN v4 or even VPN v6 configuration, it will be pretty straightforward for you guys to do that, right? So that's it from my presentation. Uh, I will allow you guys to ask me any questions if you have. Just a second. All right. So if you have any question, you can let me know into the chat. And also, if you are interested, you can definitely click on the first link to buy the course, and it will be very dedicated, detailed course. We will go all the way up to route switching, routing. We are going to cover advanced technologies, IP services. We are going to cover SD-WAN, SDA, which is the Cisco DNS Center, and programmability, including the Python and RESTCON and NetConf. So, including the labs. So everything will be covered. We will provide you the OVA that you need to do everything, all the emulation that I was doing. So it's not a simulation, it's emulation means we use the actual iOS images at the back of EVNG, and we remove all your headaches. You don't need to find the iOS images. You don't need to install the licenses. You will get an OVA package which you can import in VMware, and you will have ready to use topologies for your practicals, right? So every week I'll give you new labs, and I will solve those labs in the Zoom session after a detailed theory session, and then you will have to do the same labs again so that you can solidify your understanding and bridge any gaps that you might have in your CCI journey. So if you're interested, definitely click on the first link, Zero to Lab live only, as you see into the chat. Or if you want to discuss more, if you want more detail, you want to discuss with Christian, you can click on the second link, which is to book a meeting with Christian, and he will be more than happy to answer all your queries if you might have, right? Yeah, so SD-WAN definitely we cover in our CCI course. We have the complete SD-WAN solution. We actually have the full lab just like the CCIE exam. So multi-protocol labs include the SD-WAN lab also. So we will have the complete implementation, including licensing and template configuration and using the different policies. Everything will be there for that part, right? So let me post the links again, just in case if you guys missed it the first time. There you go. So the first link is to purchase the course, and second link will is in case if you need to schedule a meeting and discuss more. Don't worry, if you do schedule a meeting, it's not me that you need to purchase anything. If you're still making up your mind, definitely go and talk to Christian, because many questions that you have, he will answer you in more detail, and there will be clarity. And then of course after that you can decide what you would like to do, right? But in case if you really like what you see, and you will actually get very in-depth training just like this, but in more detailed theoretical manner and the practical manner, then you can also click on the first link and directly buy it. So I see a question, is this going to be live or recorded? So the sessions will be weekly sessions, live session. So I will be there into the session. I'll be explaining the concept. Let's say if the today's topic is DMVPN, I'll be going into the details of DMVPN, then I'll be configuring the lab in front of you step by step. And then we will have a Q&A session. So if you have any questions from last week or from the current week, you will be able to ask me. And the whole session will be recorded. So you will have the recordings as well available for lifetime access. Although recordings will be from the previous classes, like which we had earlier as well, because it is the same class. It's a very popular class. We have many of these. So you will see the recording from a previous class, but it is the same content that you get. And the recordings that you will get will be lifetime. So lifetime access will be there for recordings. And of course, the session that we will go through will be live. All right, I see another question. When does the course start? So the course is starting next week. So that's why I'm saying that as soon as you can book, it will be better, because we have limited number of slots here. And in case if you need to get more clarity, definitely book a call with Christian as soon as possible, and then you can talk about this, right? How many weeks is this class? So this class is going to be actually total. If you see, it is going to be 24 weeks. We will go for 6 months. And the idea is to make sure that we don't have like 10 days boot camp where everything goes over your head and you don't understand anything. So we want to make sure that we start a technology, we make sure we understand it properly. We give you time also to practice it one or more time, because you will have the recordings available all the time. And we go through all the important aspects slowly. and surely. So it will be a 24-week course in this class. And I see the question, when does this course start? I think I already answered this one, that it will be starting from next week. So sooner you book it, it's better. I see a question from Skylar that are you also going to talk about DNAC? Yes, definitely. We are going to not only talk about DNAC, but we are going to understand in detail how does the SDA work, software defined access. And DNS Center is the controller of the software defined access. So that's your software defined solution for the campus side or the LAN side. And of course, we will talk about the WAN side also, which is SD-WAN. And to top it up, we have the programmability. So creating Python programs and using Python programs to send the RESTCON for NetConf requests or API requests to the routers and switches to maybe enable an interface, disable an interface, configure BGP, remove OSPF configuration. You can do many things with programmability or automation. We are also definitely going to cover all these things as well. So the sessions that we are going to start, let me actually see the date today. So the sessions will be on Tuesday evening, every Tuesday evening, the new session that we will be starting. So it's actually from the next week, 14th, we are going to start this. So every Tuesday evening, it will be 10 p.m. Eastern. 10 p.m. Eastern is the time for that. So Tuesday evening, 10 p.m. Eastern is the time. So every session will be 2 hours, and in these 2 hours, I'm going to explain you the theory of a particular topic, and followed by a lab, and then you will do the same lab again within the live session, and every session will be 2 hours like this. And then, of course, the same lab that I did, I'm going to send you that lab on email, and you will already have the EVNG setup ready with you, so you will be able to practice that lab. And I'm also going to send you the solution file along with it, because the objective is not to test your knowledge the immediately after I teach you something. We want to solidify your understanding so that you need more and more practice. So you can feel free to look at the solution file. If you get stuck, just make sure you complete the lab as many times as you feel comfortable with, right? So the session duration will be 2 hours every week, but then during the week you can do the lab as many times as you want, and then you can also ask me any questions if you have regarding that. So we are also deciding, maybe we will keep it 2 days a week. So this is something that you can discuss with Christian. You can actually book a call, and he will give you the little bit more detail about the exact scheduling when we start. Okay. In case if you decide to purchase today or within this few hours, then you will see that there is a huge discount. You can click on the first link and you will see that discount that you are not going to get if you purchase it later after the class starts or next week. So it's better to take your decision faster. In case if you need more information, I think it's better to go for a call with Christian and then make a decision. So you can also click on the second link and schedule a call, right? So any other question, guys? Or we are good? All right. Thank you. Thank you, everyone, for joining. And I hope to see you into the class. Bye bye. Have a good night.